Okay, up to now in projectiles we've considered something that's been thrown vertically upwards. But now what we're going to look at is when something is thrown horizontally and then it falls, like a stone being thrown off a cliff or something like that. And what we do for that is we always consider the vertical and the horizontal motion separately. We treat it in two parts. And if you break it down into vertical and horizontal motion, and then we'll put them together towards the end, then you should be able to do every question on this. So here's an example. A particle is projected horizontally with speed 15 meters per second from a point 24 meters above a horizontal surface. Calculate the time taken for the particle to reach the surface and the horizontal distance travelled in that time. Now you see what's going on here. Here's our particle, and you know, if maybe it was called a package or a stone, something like that, maybe we might model our stone as a particle, might be one of our modelling assumptions, but it's projected horizontally with a speed of 15 meters per second, and it's going to sort of follow this path as it comes down and eventually hits the ground. So what we're going to do is consider in two directions, the vertical motion and horizontal motion. Because it's only ever travelling downwards, not up, I'm going to treat down as being positive. And so let's look vertically. Well, the acceleration is due to gravity vertically, so our acceleration is 9.8. Our displacement, well, it's going to go down by 24 meters, and down is positive here, so it's positive 24 meters. And here's the crux here. When it starts, yes, it does have a speed 15 meters per second, but that speed initially is always going to the right. It's horizontal. There's no vertical speed, so its initial vertical speed is 0. So using s equals ut plus a half at squared, our UVAT's equation, we can fill that in and we can find out what the time is. And the time here is 2.213 seconds. Okay, our final answers are to 3 significant figures. You see I've been more accurate in the middle of this. We would give our final answer then to 2.21 seconds, but when we use that in the next part, we'll still use 2.213 because it asks for the horizontal distance travelled in this time. And horizontally, now we've looked vertically, as there's no horizontal acceleration, it is just projected at 15 meters per second. There's no deceleration horizontally, there's no acceleration, it just goes at 15 meters per second horizontally. And so, again, you could use your s equals ut plus half at squared, but even easier just to see the distance horizontally is the speed times the time. The speed was 15, and we've just worked out that that was 2.213 seconds. And so overall the distance was 33.19 meters, or in an exam question we'd round that finally to 33.2 meters. Second example, same sort of thing. Particle is projected horizontally with speed 19.6 meters per second. Find the distance from its starting point after 1.5 seconds. So again, we're going to split it vertically and horizontally. And a quick wee diagram to start with is always good. Here's our starting point. We see that our speed is horizontal and it's going to end up down here after so many seconds, after 1.5 seconds. And what we need to do is find out, well, what's this vertical distance, y? What's this horizontal distance, x? And then we'll be able to work out the distance from its starting point. So again, vertically, really easy in this again, that a is 9.8. It's always going to be under the influence of gravity here. The acceleration is due to gravity. And its starting velocity vertically is 0. All the speed is horizontal speed. There's no vertical speed. So the velocity here is 0. The time is 1.5 seconds. And so again, using s equals ut plus a half at squared, we can work out that this value y is equal to 11.025 meters. Horizontally, the distance is much easier. Distance is speed times time. We have s equals ut plus a half at squared. But we know that horizontally there's no acceleration. So that's always going to be 0 horizontally. So s equals ut, the speed times the time. So 19.6 times 1.5 is 29.4. And so using Pythagoras' theorem, if this is 11.025 and this is 29.4, we can find its distance from starting point to be 31.4 meters. This example, a stone's thrown horizontally with a speed of 20 meters per second. So again, it's thrown horizontally. We've got our initial speed of 20 meters per second. By modelling the stone as a particle, and that's a very common assumption or a modelling assumption that we make. Another one would be maybe that there's no air resistance, or that the stone moves in one plane, it just goes that way, it doesn't flitter about while it's moving. Sometimes we'd even say that the acceleration due to gravity is constant, but the main one is that we treat the particle as a stone, or there's no air resistance. But we're asked to find the magnitude and direction of the stone's velocity 2 seconds later. Okay, so again, had this stone been thrown, this is the path it's going to take, and at some stage, 2 seconds later, there it is. Now it's going to have a horizontal velocity and a vertical component to that velocity, and that's what we need to find. Again, we're treating down as being positive because all the motion is coming down vertically, so treat that as positive. So the acceleration due to gravity is positive 9.8. Again, u is 0, and we're told we're dealing with 2 seconds later, so t is 2. And so if we use v equals u plus at, very, very quickly we see that the velocity is 19.6 meters per second vertically. Horizontally, we say the horizontal velocity is always 20 meters per second, it just keeps going across here. So this component u is 20. Now again, if we use Pythagoras' theorem and trigonometry on that, here's what happens. It's going 20 meters per second to the right, it's going 19.6 meters per second down. So Pythagoras' theorem will tell us then that the overall resultant, the overall magnitude of the velocity is 28 meters per second. And trigonometry then will say, okay, if we treat our opposite as 19.6 and our adjacent as 20, we say that theta is 44.4. And so just to sum it up, the stone's velocity is a magnitude of 28 meters per second at a direction of 44.4 degrees below the horizontal. Very important to give that as a reference.